Velocity is probably one of the tougher ones. That's why we're going to give it a couple of days. Um, there's just a lot of information. So let me just say, first of all, velocity is the rate of change of displacement. But we can talk about velocity in a couple of different ways. The first is average velocity. So there's going to be two different types. Average velocity is just the change in displacement over the change in time. I'm going to write it the change in S over the change in T. The other way you might think of it, if you look at this graph, I'm going from this point to this point. The average velocity is the slope of the endpoints. Okay? So maybe think of it this way. When you drive, say, to Cedar Rapids, think about what would your average velocity be. You take how far it is to get to Cedar Rapids divided by the time it took you to get there, and it gives you an average speed. That includes stopping at stoplights. It includes slowing down for different things, speeding up. So you get an average from point A to point B. So the first thing you're going to do when you find average velocity, if you're doing an equation, you find the endpoint for point P, the endpoint for point 2, and whatever those coordinate points are. So your T1 and your S is this way, 1. This is T2, S2. You just minus your Y's, minus your X's. Because remember, when you find slope, it's just the change in Y over the change in X. That's what average velocity is the slope of the endpoints. Slope of endpoints. Now, your average velocity when you drive to Cedar Rapids is much different than your instantaneous speed. So like when you're passing the Brandon exit and you look at your speedometer, how fast are you going at that exact moment? Your instantaneous speed is different from your average speed. Your instantaneous speed, your velocity function, is the derivative of your position function. All right, so if I come back here, where your average speed is this along here, your velocity instantaneous is at this exact moment. What's the slope of what's the gradient of the tangent line? So we're going to talk about two different things. If it says average, you're going to find the slope of 2 points. If it says instantaneous or just plain old velocity, you're going to use the derivative. These bullet points are also important. If the velocity is positive, it's moving to the right or up. If it's less than 0, negative, it's moving to the left or down. And when your velocity equals 0, it is at rest or changing direction. Okay. Oh. When we calculate displacement, you're going to talk about the rate in meters, and time is usually in seconds. So the units for velocity, meters per second, or we just, in IB, we just move the S up, meters per second to the -1. Okay. So this actually distinguishes the difference between the average and the velocity in the instantaneous. So we have an equation. If I want to know average from 2 to 5, I have to create 2 points. So that means I have to find my Y value or my position. So what is S of 2? If I plug 2 in for my t, I get 2. So that coordinate point is 2, 2. Then I plug in 5. 3 times 5 is 15 minus 25 is negative 10. So for letter A, the average velocity is my change in y minus the y's over my change in x. So that's negative 4 meters per second. This is my average velocity, the slope of 2 points. B, the instantaneous velocity means I have to find the derivative of my position function first. The derivative of 3t is 3. The derivative of t squared, going back to derivatives, so be careful. Then I find v of 2. At 2 seconds, how fast is the particle moving? Negative 1 meters per second. So notice between 2 and 5 seconds, it travels at a velocity of an average of negative 4 meters per second, but exactly at 2, it's only traveling at negative 1 meters per second. Okay, so you're just I just copied this down. All of this down, I didn't write the little print, but the blue stuff, differentiate is the word for derivative, integrate is the integral symbol, and do this. So you might want to pause the video. All right, distance traveled, you're really just going to need this right here. Distance is always positive, so we always have to consider distance traveled. We have to make the velocity positive. So many times if we have a calculator available, we will just make the velocity the absolute value so that it is a positive value, which is our speed. Because we're not guaranteed to always have a function all above the x-axis. So this way, this guarantees that it's going to make everything positive. Okay, so for example 3, the very first thing you should always notice is what is the graph of. In this case, this is a velocity graph. Find the total distance traveled. Notice the entire thing is above the x-axis, so everything's positive, so that's good. So since the graph is velocity, to find distance, I just need to find the integral from 0 to 0.6 of my velocity. And what is this represented by in the graph? We just need to find the area between the curve and the x-axis. So what I did is broke it up into chunks. And I just found the individual area of each piece. This is a triangle. I used 1/2 base times height and got 2.5. This is a rectangle. So base times height, I got 10. This is a trapezoid. Remember your trapezoid formula, h over 2, base 1 plus base 2. This is 4. This is another rectangle. This is 3. This is a triangle on the end, 1.5. So since I can find the area of each of those individual pieces, my distance traveled by the train just equals each of the areas added together. The train traveled a distance of 21 kilometers. I'm going to apologize right now. I did not give you near enough room. You might want to use, you're going to need all the space kind of above and around this problem. Okay, so let's start with A. It says find the times when P reverses direction. All right, so the first thing we're going to do is find when the particle is at rest, when the velocity equals 0. So I just take my original function, it's the velocity function, set it equal to 0. Then I can factor it.
Stefan Robinson to the office. Stefan Robinson to the office.
So the two values in which when the particle changes direction is at time 1 and time 2. Now, this is looking for the first 4 seconds. So what I'm going to do, what I need to figure out here is what direction is this going every time it changes direction. And I'm going to start at 0. And because the problem is a whole, normally it would start with time in between 0 and 4. Generally, it's more specific. We're going to do this for this whole problem, though. So everything, this is going to be my velocity. I'm going to talk about this from 0 to 4. And I'm going to look at each time it changes direction. So I want to see from 0 to 1, is it going to the left or to the right? So say I plug in a half in between this interval. If I plug in a half, this is going to be negative, and this is going to be negative, and a negative times a negative. My velocity function will be positive. Then if I look in between 1 and 2, so then that'd be 1 1/2. 1 1/2 minus 2 is negative. 1 1/2 minus 1 is positive. A negative times a positive, this velocity will be negative. And if I plug in 3, that's a positive times a positive, it's positive. So let's think about a motion. It's going to the right, and it's moving to the left, then it's moving to the right. That's kind of our motion picture. So think about how distance is, this is all part A, but this is going to help us for part B. For distance, we have to make our velocity positive. So let's think about right here, we have to section our integral stuff out to find our distance. We're going to do it by hand first, and then this allows us to use Math 9 to check. But we have to write it all out, and this is why this is the section that gets long. All right, so because my velocity is positive from 0 to 1, to find my distance, I don't have an area, so I just have to do my integral from 0 to 1 of my velocity function. So let's find this area here first, or this distance. So I do the antiderivative, add 1 and divide, add 1 and divide, add 1 from 0 to 1. Now, when I plug in 1, I get 1/3 minus 3/2 plus 2 minus 0. This whole thing, I'm just going to tell you, is 5/6. So between 0 and 1 second, my distance I traveled was 5/6. Now I'm going to do the same thing, but from 1 to 2, this is going to give me a negative value. So I'm going to go from 1 to 2 of the, I'm just going to write my velocity. So I'm going to do this whole integral all over again. But this time I'm going to go from 1 to 2. All right, so when I plug in 2, I'm not going to do all that math. We can talk more tomorrow. But when I plug 2 in for all my t's, I get 2/3. Minus, I already know from plugging 1 in up here, I get 5/6. So if I get my common denominator, I get -1/6. This makes sense because I knew I'd get a negative number, but what is the distance traveled? My distance is always positive, so it's going to be a positive 1/6. So far I have 5/6 plus 1/6, so I've traveled a distance of 1 meter. My last thing I've got to do is from 2 to 4 of my velocity. Finding this distance from 2 to 4. This is why this is super annoying, sorry, and I didn't give you enough room. From 2 to 4. So if I plug 4 into all of my t's, I get 16/3 minus, we already know when I plug in my 2. See, here's my plugged in 2, I got 2/3. So I get 14/3. So this distance from here to here is 14/3. So this is 1 plus 14/3. So my total distance equals 1 plus 14/3 is 17/3. All right. Last but not least, letter C is the change in displacement. And so that's just the first 4 seconds. All right, I'm going to erase some of this. Change in displacement. Displacement is your position function. Displacement can be positive or negative. This is like this is super important here. So if we look at this right here, basically we're going to take our 5/6 minus the 1/6 plus the 14/3. Displacement can be positive or negative. So it ends up being 15 1/3. So this was 15 2/3 if we write that as a mixed number. This is 15 1/3. Your displacement can always be a little bit, if it's negative, that's going to take it away. We'll talk about this in much more detail tomorrow when we can take our time.